We've been talking about biostatistics, and in this lesson we are going to focus in on analysis of discrete data, and specifically how to calculate and interpret chi-squared test statistics and their associated p-values. For the discrete data, the chi-squared test is used to determine if frequencies differ among categories within populations. This is easier to understand with an example. This is an example that I'll introduce and you'll have an opportunity to work on later. And this looks at the number of documented rabies cases in animals in one South Carolina county, specifically Lexington County near Columbia. And many animals were presumably brought in for testing. Out of those animals brought in to state testing labs, 40 bats were determined to have rabies, 6 raccoons, and 4 foxes. The large discrepancy in numbers here suggest that it is not equally likely for bats, raccoons, and foxes with rabies to be brought in, but rather bats are more likely and the other categories less so. So put another way, in our sample, the relative frequency seems to vary among categories. But what we would like to know for the general population of bats, raccoons, and foxes is, can we rule out the null hypothesis that the relative frequency of encountering these rabid animals is actually the same among all 3 of these categories, and it's just by chance alone that in this particular year they happen to collect more bats and fewer raccoons and foxes with rabies. So is this variation due to chance alone, or is this actually due to some difference in the rate of rabies among the 3 different groups listed? We will look at this using the chi-squared test, and that is abbreviated as shown here. So the chi-squared test is commonly used to determine statistical significance of count data. So data that is recorded as counts of individuals. And to perform the chi-squared test, we will need to know both the number of individuals we observe in each group, as well as some expected number in each group under our null hypothesis that there's really no difference in relative frequency among the various groups we are analyzing. So here's the formula, and we'll look at this on the next slide. What you can see is that before we can apply the formula to calculate a chi-squared value, we need to know the number of observations in each category, as well as the number of individuals we would expect in each category under the null hypothesis. And so now let's look at this formula in more depth. What we're calculating here is a chi-squared test statistic. It's our chi-squared value. The number that we get out of this calculation is not actually a p-value, but we can use our chi-squared test statistic as well as another number called the degrees of freedom, which we'll talk about in a couple minutes. We can use those 2 numbers to look up on a table p-values, and the p-value is typically the number that we really care about. So now let's look at how we calculate the chi-squared test statistic. First, you can see that we have this sigma here, and the sigma is telling us that we will need to sum from I equals 0 to n. That's really a fancy way of saying we need to sum across each of our different categories. In our rabies example, we have 3 different categories. So here we'll need to sum across all 3 categories the number of observed individuals in that category minus the number that we would expect if the relative frequency was the same across all categories. And so that's the number that we'll have to calculate. And then we will take the difference observed minus expected. You can see that's in parentheses. Whatever that difference is, we will need to square it. After we've squared it, we need to scale it by dividing by the number that were expected. So our overall formula then is observed minus expected squared divided by expected. And we will calculate that separately for each category, and then because of this sigma, we'll add all of those different values together. Those added values will give us our overall chi-squared value. I will not do that math for you for the rabies example because I will save that for you, but we will go through the math step by step for this example of a monohybrid pea plant cross. This is a cross that we expect to show simple Mendelian inheritance with one dominant trait, one recessive trait, and the ratio that would result. So presumably we had some true breeding green peas and some true breeding yellow peas way back in the parental generation, and those were crossed together to make F1 plants. Those F1 plants were then allowed to self, and the resulting seeds were collected. Those seeds now represent the F2 generation. 880 seeds from the F1s were collected. Again, these are the F2s now. And out of those, we found 639 green and 241 yellow. These are our observed data. If we look at a Punnett square, if green must be dominant and yellow, or little g, must be recessive, given how many more green plants we found than yellow, if this is a simple Mendelian trait. And so we are going to set up this Punnett square as shown, and you can see that 3 out of the 4 categories are expected to result in green seeds, because both heterozygotes and homozygous for green will give us green seeds, but there's only one way to get yellow seeds, that is the double recessive. So we expect only 1/4 of seeds to be yellow. Well, if we have 880 seeds, then 1/4 of 880 is 220. So our expected number of yellow seeds is 220, and 75% of 880 equals 660. So we expect 660 green peas. We can do an eyeball estimate here, or a quick estimate, and see that the number of green peas we collected, 639, is close to our expected, as is the number of yellow seeds close to our expected number of yellow seeds. However, they are not exactly the same. And what we would like to know is this difference between observed and expected in both cases large enough that we can rule out the null hypothesis that the difference between what we observed and what we expected is just due to chance. If it's not due to chance, then we can rule out this being a simple Mendelian trait. Or, in this case of a monohybrid cross, if we cannot rule out the possibility that this is a simple Mendelian trait, then that is probably the simplest explanation for our data, and we will continue to accept the idea that inheritance here is simple Mendelian. So this is a sort of unusual case where by not getting a strong p-value, a p-value of less than 0.05, we would actually be able to keep our hypothesis that, in this case, that the inheritance is simple Mendelian. Let's go through the steps of this calculation. We've already looked at our observed numbers, and I talked to you about how you would calculate the expected for this particular trait. Now you can see that we've put those numbers into a table, and this table is going to help you organize calculations and make them much easier to keep track of and therefore to get correct. So for any chi-squared test that you have to calculate by hand, I would strongly recommend that you make a table like this. We have the green peas in the first row, yellow peas in the second row, the observed and the expected values. Well, to do our calculation, remember the first calculation in parentheses is observed minus expected. So if you subtract those numbers, you get -21 for green and +21 for yellow. And you'll see that these numbers should always sum to 0. That's a good way of checking your math. They do for us, so far we're in pretty good shape. Now, our next calculation is to square what's in parentheses, or to square this difference between observed and expected. And so negative 21 squared becomes positive 441. Note that the negative sign goes away. And positive 21 squared, of course, also equals positive 441. So those are our two observed minus expected values. Now in each case, we have to divide by the expected value. And the expected value for green was 660. For yellow, it was 220. So you can see 441 divided by 660 equals about 0.668. And 441 divided by 220 equals around 2 with some rounding error. So we've calculated this for each of our categories, but this sigma tells us we have to add up those numbers. So 0.668 plus 2, of course, equals 2.668. That is our chi-squared test statistic. We now can use that to determine the p-value if we know one more number. And the additional number that we need to know is the degrees of freedom, or abbreviated typically as df, and that is going to equal n minus 1. N is the number of categories for a simple chi-squared test, specifically a chi-squared test with only one category of variables. Then the degrees of freedom equals the number of categories minus 1. You will learn at some point about more complex chi-squared tables where the calculation of numbers of degrees of freedom is a little bit more complicated. But in these simple examples, it will be n minus 1. Now we have our two values, the 2.668 and our degrees of freedom. We now will be able to look up the probability. And this is a table of chi-squared values. I'm going to show you how the table is set up. Along the different rows, so over in the left column, is the number of degrees of freedom, going from 1 at the top up through 5 on this table as we progress, and of course the table could be larger. Across the top we have different probabilities, and we focus on the ones that are either very high, so nearly 100%, 0.95 and 0.9, or down here at this end, probabilities that are very low, 0.1 or 0.05, 0.01, etc. Now typically with inferential statistics, we want to reject a null hypothesis and say that something else besides chance alone is what's going on. So typically when we are doing a chi-squared value, then p-values of 0.05 or lower are desired. Notice that the trend for how our chi-squared values change as p-values get smaller and smaller. You can see here the chi-squared value is very, very small, very near 0. And as the p-value gets smaller and smaller up in this row, the chi-squared number gets larger and larger. So we will have a greater chance, or a greater, we will have a smaller p-value the larger the chi-squared value is. By convention, scientists typically say that p-values of less than 0.05 are statistically significant, and values above that are not significant. And so that will be our typical cutoff for declaring something significant. Let's just go over one more time the meaning of p-values before we look at our results. The p-value, remember, is the probability that our observed result, or an even more extreme result, would occur if the null hypothesis is correct and there's no real difference among groups except that due to chance alone. If the p-value is high, we cannot rule out the null hypothesis that chance alone is the only cause. However, if the p-value is small or low, we become more confident that our treatment variable in some tests, or in the chi-squared test, the difference in relative frequency among categories is not due to chance alone, but there is something else that must have caused the result. Remember that if p is less than 0.05, we can say the result is statistically significant and the hypothesis is supported. We don't talk about proven, but we can say it's supported at these values. Typically, at p-values greater than 0.05, we would say the result is not significant, or the hypothesis is either refuted, or sometimes we would say not supported. So now let's go back to our pea plant example, and we'll talk about why this is a bit of an unusual case. So remember, we had the green and yellow seeds, that's two colors, or two categories, and 2 minus 1 equals 1. So we had 1 degree of freedom. We had a chi-squared value of 2.668. So let's see where that would lie on this table. Here is our 1 degree of freedom, and if we follow the table this way, 2.668 is somewhere between 0.2 and 0.1. So we know that our probability for a deviation as large as we found, or larger than we found, if chance alone was the only thing causing that deviation in our number of observed green and yellow seeds, is somewhere between p equals 0.1, somewhere greater than that, and it's somewhere less than p equals 0.20. So in this case, remember that our null hypothesis was based on an expectation of a 3-to-1 ratio, which we derived from our Punnett square, and then we said, plus that might be influenced by chance alone. We cannot reject our null hypothesis that this ratio plus chance alone is all that we need to explain our results. What this means then is that simple Mendelian inheritance could explain pea color in this cross. We do not need to invoke a more complicated genetic mechanism to explain it. So in this cross, that is a good outcome. In many other chi-squared examples, our null hypothesis is less interesting. It is simply that there is no difference among groups and that they all have similar relative frequencies with deviation occurring by chance alone. In those other situations where the null hypothesis is less interesting, then a failure to reject the null hypothesis means that we have not shown that there is a meaningful difference among groups. So let's go back as an example and look at the rabies cases in Lexington County, South Carolina. Here we saw that there appears to be a higher relative frequency of bats collected with rabies than raccoons or foxes. And what we'd want to know here is this difference real? Can we reject the null hypothesis that the relative frequency is actually the same among these groups? If we can reject it, we could say that bats actually have a higher relative frequency. To determine that, you will need to do calculations to determine the expected number of animals in each group that would be found with rabies if this variation were due only to chance alone. After determining that, you will need to calculate the chi-squared statistic using your observed minus expected squared over expected formula for each category, summing those values, and then determine your degrees of freedom based on the number of groups, minus 1, and then you will need to look up a p-value for that on a chi-squared table. And there should be a series of questions that allow you to go through those calculations now. To return to our learning outcomes, in the previous lesson, we talked about many of these topics that are grayed out here. In this lesson, we focused in specifically on discrete data, and we went over how you can calculate and interpret chi-squared test statistics, as well as p-values.